Okay, you must submit your assignments to my mail ID. Okay, mail ID is known to you. तो लास्ट लास्ट टाइम तो मैं दिए थे मेल आईडी, मुझे मुझे मेल कर देना एंड मैं उसी से अटेंडेंस दे दूंगा.
ओके सर. सर मेल आईडी एक और बार मिल सकता है क्या सर?
Are you in the WhatsApp group?
यस सर, आई एम इन द व्हाट्सएप ग्रुप.
अच्छा, उसमें मैं शेयर कर देता हूँ एक बार. ठीक है.
ओके सर, थैंक यू सर.
ओके. इथरे तमे सेथिरे मैं एइथरे WhatsApp रे पचारथिल तो मोबाइल ले करथिली तो मु आ रिप्लाई दे पान नथिली. तांको देखा जिवो ना स्क्रीन टा. କିଛି ଷ୍ଟାର୍ଟ କରିଥିଲ? ମୁଁ ସେଟାର କଣ କି ଗୋଟେ ନୂଆ କରିବି ବୋଲି ମୁଁ ତମକୁ ଏକାଥରେ କରିକି ନୂଆ ତମକୁ ଦେଇଦେବି, ମାନେ କିଛି ଗୋଟେ ଆଡଭାନ୍ସ କରିକି. ହଁ, ମଡେଲଟା କିଛି ଗୋଟେ ଚେଞ୍ଜ କରିବାକୁ ପଡିବ କାହିଁକି ନା ଏଲଏମଏଫ ଟା ଅଲରେଡି ये शेयर कर देना मेरे से.
not equal, than equal, than less than equal. Similarly, overloaded logic operators like not, and, or, NAND, NOR, XOR, and ignore. Similarly, overloaded shift operators, that is shift underscore left, shift underscore right, rotate underscore left, rotate underscore right. SLL, this we have discussed. SRL, ROL, ROR. As you know that SLL, this stands for shift left logical. SRL, this stands for shift right logical. ROL, this stands for rotate left. ROR, this stands for rotate right. So this plus and minus, these operators are used with unsigned operands, that is 0 or positive, unsigned operands of different lengths. So the shortest operands will be extended by filling zeros. Okay, like I am saying, if suppose here you can see that you want to add 1 0 1 1 plus 1 1 0. So this is the shortest operand having 3 bits. Here this is having 4 bits. So what we'll do, so that shortest operands, so now this will be filled with zeros from left. So this is 1 1 0. So here 0 will be added in the left. Now, so this will be added. So now what will happen is, if any carry will be there, this carry will be discarded so that the result has the same number of bits as the longest operand. Now in these two, when A equal to this, let's say this is A equal to this, let's say B equal to what, that is 1 1 0. Okay. Let's say A equal to 1 0 1 1. B equal to 1 1 0. Now, what happens? You can see that here this is having longest, that is 4 bits are there. Here this is 3 bits are there. The result will be of what? 4 bits. Any carry will be discarded. So now it will add this, like it will become what? 1 plus 0, that is 1. It will add these two. 1 plus 0, 1. Now 1 plus 1, that is 0, carry 1. So it will come over here. Now this 1 plus 1, 0, carry 1, it will come over here. Now this 1 plus 1, 0, it will be having a carry 1, but this will be discarded. Only you are considering the result of 4 bits. Okay, so here any carry is discarded so that the result has the same number of bits as the longest operands. Like here we are considering, so this 1 0 1 1 plus 1 1 0. Now 0 will be added here without this, and the result is what? 0 0 0 1. And the carry is discarded. So this carry is discarded. And your numeric bit package, this provides overloaded operator to add an integer to an unsigned. We can add an integer to an unsigned by numeric bit package. We can use the concept of operator overloading. But we cannot add a bit to the unsigned type. These are integer, we cannot add bit, that is a binary digit, to an unsigned type. Now you see here, this is the example. We're taking, if let's say A and B are unsigned, then if A plus B plus 1. So this is allowed, but the statement of the form sum equal to A plus B plus carry, this is not allowed, because this carry, this is what? Bit. That is either 1 or 0. That is a bit. Yes. Okay, this 1 you can add, but this carry it cannot add because the carry is of type bit. Okay, now when we want to do this, your carry must be converted to unsigned. Here this A and B, these are unsigned. So this now this carry must be converted into unsigned so that we'll be able to add those. So there is a notation unsigned 0 implies carry. You can see. So this you can use, which will now after that we'll able to add this. So 0 implies carry. So this you can use so that now that will be converted into unsigned and you'll be able to add that. So now you can see this following BSDL code. So here you can see that already we discussed this, that here we are using the IEEE library. So you have to use this library keyword. Okay, so library keyword, then its name, IEEE, then semicolon. Then we are going to use this numeric bit. So use keyword IEEE.numeric_bit.all, semicolon. Then now you see this example of this 4-bit adder, which we already discussed. So now this same code of which we have already discussed. Now here we are using this IEEE library, and here you see that there what you have done, just I'll open it. Okay, so this was the code for a 4-bit adder. Okay. Now you see the difference. So there we are using bit vectors, which we have already discussed. There we have used this bit vector. Now you see this is similar to that. There we are using this entity keyword, entity. Then okay, entity, then entity is the keyword, then entity name, that is adder4, then each keyword. Then you have to declare the port. We'll write this port keyword. Then as you know, this A and B. Okay, so these are what? In, that is mode is in, and type is bit vector, there we have taken. And here you can see that type is unsigned. Okay. Here unsigned. So their type is bit vectors. Now this is what type is unsigned. So rest 3 down to 0. There you are using. Now this CI or carry in, this is what? This is of type bit. This is similar, that carry in, this will be always a bit. So carry in CI, mode is in, type is bit. And here you can see this output as out. Instead of bit vector, here we are using this unsigned 3 down to 0. This is carry out is again same out bit. And this is the end of adder 4. That is entity name is adder 4. Then similarly, here you can see the architecture. The architecture name is overload, then of keyword, then entity name is, entity name is adder 4 is. Then this signal, there you have written what? T is the internal signal which was of type bit vector. But here you can see that the name we have taken sum5. Okay. So sum5. That you know, actually when like in the previous example, I told that when we are adding this becomes actually 5 bits, right? 4 bits sum and 1 carry out. Okay. So that's why here we have written this sum5, signal name we have taken sum5. Okay. So which we have taken what? Equal to 0 and this. Okay. So initial this is 0 and the 0 concatenated with this. You can see this ampersand stands for concatenation. So 0, this ampersand A plus B plus unsigned 0 implies Ci. As you know, this is used for what? Already we discussed. So 0 implies carry. This we saw that this will do the conversion. So this will do the conversion of bit to unsigned. As you know, these A and B are unsigned. So we can use notation is actually the full notation is this unsigned within parenthesis. You can see 0 implies carry. So unsigned within parenthesis. Unsigned within parenthesis 0 implies Ci. So this will convert this to unsigned. So this carry in or Ci. So Ci this will be converted into unsigned. That this bit will be converted into unsigned. So that now you can add those. Okay. Now this is or sum. This will be called what? Sum 5. Whatever adding sum 5 3 down to 0 means these 4 bits. So this will be considered as the sum. As you know. So this will be considered as the sum. S. So S is nothing but this. And your carry out or CO. So this will be called what? This you can see sum 5 4. That is the most significant bit. So this is the 0 index. This is 1. This is 2. This is 3. So sum is what? Sum 5 3 down to 0. Then next is that is CO carry out. So this is nothing but this. That is the most significant bit. That is the index 4. Okay. So these are having the index first 0, 1, then 2, 3, then this is the index 4. So this is the LSB and this is the MSB. Okay, so S will be sum will be equal to this, and your carry out or CO this will be equal to what? The MSB, that is sum by 4. Then end keyword, then you write this architecture name, that is the overload. Now one version of Xilinx synthesizer, this produces the result. You can see the same thing. Here Xilinx synthesizer. So here A, you can see we have written what 3 colon 0 4. That is here. You can see this is your nothing but your A. This is nothing but your B. So indexes. The indices you can see from 3 to 0. B from 3 to 0. Okay. Then here you can see the sum. So again that is from 3 to 0. And this is the carry out. See. So there are various useful conversion functions which are found in the numeric underscore bit package, which is you can see 2 underscore integer A. This what it does, it converts an unsigned vector A to an integer. Similarly, 2 underscore unsigned B comma n. So this converts an integer to an unsigned vector B of length n. Similarly, another you can see the conversion function unsigned A, which causes the compiler to treat a bit vector A as the unsigned vector. So this bit vector A, this will be converted into unsigned vector. Then bit underscore vector B, this causes the compiler to treat an unsigned vector B as a bit vector. So this B will be converted into bit vector. Okay. If you are using the multi-valued logic, so you can use the IEEE standard numeric underscore std package. The numeric underscore std package instead of using this numeric underscore bit package. So you can see here, like we are using this library keyword just here. Okay, so actually this will be in a bold letter. This library is used as a keyword. You can use this library in bold letter, the library keyword, then IEEE semicolon. Then want to use this standard logic, use IEEE.std underscore logic underscore 1164.all. Another is use IEEE.numeric underscore std.all. These are also keywords. So just write in bold letters. Okay. Now you see the BSDL code for the 4-bit adder. This we are rewriting whatever we have written here. So this is rewritten by using standard logic std underscore logic underscore unsigned package. So this package provides the overloaded operator to add the standard logic bit to a standard logic vector. So where will not need the type conversion. So just see here, like here, what we discussed, we are using this library IEEE, then use this IEEE.std underscore logic for 1164.all. Use IEEE.std underscore logic underscore unsigned.all. Then you can see this description of adder 4. The entity adder 4 is entity keyword, then this name of the entity is adder 4 is keyword, then the description of port. So you can see the difference here. What I have written, port AB in unsigned 3 down to 0. Okay. Now here what I have written, instead of unsigned, here we are writing what? std underscore logic underscore vector. So standard logic vector 3 down to 0. Then CI as usual means this is what mode is in, but again the type you can see that we are using standard logic std underscore logic, that is standard logic. There you are using what? Bit. Okay. So there bit, here it is standard logic. Now the output S out here. Now you can see that there what we are using this unsigned. Now here we are using the standard logic vector. So std underscore logic underscore vector 3 down to 0. Similarly, CO mode is out. Instead of bit, we are using standard logic. So std underscore logic. Now and keyword, then can write this entity name, that is adder 4. Then the architecture description. You can see architecture name is we are giving overload, then off keyword, then entity name is adder 4, then each keyword. Then the internal signal, you can see that signal keyword we are using, that is what? Sum 5. So again you can see here sum 5. This one, sum 5, here we have written what? Unsigned 4 down to 0. So instead of that, we'll use what? Standard logic vector, that is std underscore logic underscore vector 4 down to 0. Now within this begin and end, you can see that sum 5 equal to 0 and a plus b plus ci. Okay. So here you can see that this type conversion is not required. In the previous example, previous BSDL code, here you can see that here using this type conversion, we are converting this bit into unsigned. But here this is not required. Directly you can write this CI. Okay, no need to convert that here, because here you are using what? Standard logic. So no need to convert that. So here we are using this package provides the overloaded operator to add a standard logic bit to a standard logic vector. So these are standard logic vectors, that is A and B are standard logic vectors, and CI is the standard logic bit. So we can add the standard logic bit to a standard logic vector where the type conversion will not required. But here the type conversion is required. Rest here you can see that s equal to sum 5, 3 down to 0, same as this, 0 equal to sum 5, 4, then end keyword, then the architecture name is here overload, end keyword, architecture name is overload. So this is the BSDL code for a 4-bit adder using the standard logic unsigned package. Okay, so we discussed this BSDL models for from multiplexers, that is using concurrent statements. So you know that for multiplexer, this is the equation. Okay, this is the logic equation and the corresponding BSDL statement. Okay, so we discussed 2 to 1 multiplexer. This cascaded multiplexer we saw, and how we are writing the conditional signal assignment depending on the condition. So depending on the value of the control, here as I told that control input. So that is depending on the control input, depending on the value of control input, how we are getting the output. How we can write this conditional signal assignment. In case of 4 to 1 multiplexer also we saw how we can get the output using this conditional signal assignment. And how we can use this with select. Okay, we saw how to use this while and how to use this with select. And in case of process, we can use this case statement. We are using this processes for describing the multiplexer. So we can use this case statement. Then discuss the BSDL library. So BSDL code we saw for the 4-bit adder using unsigned vectors. And another we saw that for the standard logic unsigned package. Okay, one more portion is left, that is modeling registers and counters using BSDL processes from chapter 2. So this is 2.12, 2.13, only 2.14 is left from chapter 2. And that will complete tomorrow. And just stop sharing. Okay, all of you tell your registration number. Singh, Vaibhav, Singh. Anisha Swai. Hello. Siddhant Sarup Malik. Okay, tell your registration number. Okay. Okay, Vaibhav Singh. Arpan,
Sir, 204-100-2035.
204-100-2035.
Yes, sir.
Next, Asutosh, no. Subham Patnaik,
Sir, it's 20410. Hello.
yes.
It's 20410-16177.
Okay. Next, Supriti,
Yes, sir. It's 204-101-9297.
okay. Next, Katie,
Yes, sir. It's 204-101-8112.
next, Varun Paspalak,
Yes, sir. It's 204-101-6116.
okay. Next, whoever left, just tell your registration
Sir,
number.
Vaibhav.
Yes,
Sir,
I'll
20.
yes,
Yes, sir. Vaibhav, sir, 20410 22001.
okay. Next, who else left?
Sir, Arun,
Yes,
204-101-9049.
yes,
9049.
yes, then,
Animesh Abhinandan, sir.
yes, tell,
2041
yes,
001
yes,
075.
okay.
Thank you, sir.
Okay, thank you. Next, who else left?
Sir, Ananya Angita Swan.
Yes. Why you joined just now?
Hello.
Yes, tell your registration number.
204-101-9341.
Okay. Who else left?
Sir, Anisha. 204-101-9346.
2040?
204-101-9346.
Yes. Okay. Who else left? Okay, then thank you all of you. You may leave now.